Hey, let's get back to excretion. We're going to talk about excretion in greater detail right now. So what are the organs involved with getting rid of drugs and the metabolites? The main organ is the kidneys. Excuse me. Now remember, the liver is what metabolizes drugs, but most drugs are excreted through the kidneys. That's the main organ. You can also, some drugs are excreted through the respiratory tract, actually exhaling out drugs. Breast milk, saliva, sweat, bowel, biliary excretion. That's when actually the liver itself breaks down those chemicals and gets rid of them in the bile. So those are the main ones. The excretion of drugs by the kidneys is two different mechanisms. The most common is filtration of the agent through the glomerulus into the renal tubule. The drug that enters the tubule in this manner is partially reabsorbed through the wall of the tubule back into the bloodstream, which delays the complete elimination from the body. So that's really important because at any given time, a fourth of the blood is going through the kidneys. So if the kidneys are able to filter a drug out in one pass, you'd lose the drug almost immediately. So some of the medication is filtered out, some goes back into the bloodstream and continues to go around the body through distribution. And then some drugs are directly excreted through the walls of the tubule by tubular secretion. Now, the pH of the urine affects the drug excretion by changing chemical forms of a drug. So if the urine is acidified, it increases reabsorption or slows elimination of weak acids. If the acidification of urine decreases reabsorption or increases elimination of weak bases. Remember, acids and bases, that's from chemistry. Acids are things with a low pH. Bases are things with a high pH. So if your urine gets more acidic, because it's more acidic, it will slow excretion of weak acids, but it will increase the elimination of weak bases. Now we talked about this also briefly. Half-life. Half-life of a drug. Half-life is the amount of time it takes your body to get rid of half of what was originally ingested or injected or given. And this is how drugs are measured. Remember, you'll never see something that says it will always go, your body will get rid of a drug in 1 hour or whatever. It will say half-life is thus and such. So, half-life is, remember, if the half-life is 1 hour, that means in 1 hour your body will get rid of half of what was taken in. In the next hour, it'll get rid of half of what's left. The third hour, half of what's left. It generally takes 4 or 5 half-lives to really get the concentration down low enough that it's negligible. So, if the half-life is 4 hours, how much is remaining? Well, how much is in the body immediately after injecting that morphine? Let's just say we're using IV or an intravenous morphine. That's a parenteral medication. So immediately, 100%. After 4 hours, how much is left? If the drug's half-life is 4 hours, after 4 hours, you're down to half of it. In the next 4 hours, you're down to 1/4 of what was initially injected. After 12 hours, 12.5%. After 16 hours, 6.25%. After 20 hours, you're down to about 3%. 24 hours, down to about 1.5%. So that's half-life. Key concept. Remember, so drugs are not excreted at a constant rate. It's a decreasing amount because it's based on concentration. Remember, drugs that are given in a higher concentration are absorbed very rapidly. So consequently, high concentrations are excreted rapidly. And as they're excreted, the concentration drops, and so they're excreted slower and slower. Does that make sense? Concentration is key here. High concentration means it absorbs quickly, gets rid quickly. But as you get rid of it, your body gets rid of it slower and slower. Now, pharmacodynamics is another key phrase here. Pharmacodynamics is the study of biochemical and physiological interaction of drugs. And the study of biochemical and physiologic interaction of drugs. So that's pharmacodynamics. Drugs do not create new cellular functions, right? But it changes existing functions. So drugs can interact with the body with several different ways. Some drugs have a molecule fits into a specific receptor, will create a specific response. So let's say this is your let's say this is your cell. A drug that comes in like this will fit in just one way, but a drug that comes like this, okay. I told you I like to use my hands. But drugs don't create new functions, but they do change functions. So drugs can, suppose we look at antidepressants. Antidepressants don't change how the brain physically functions, but it changes how the current cells react in the environment. So pharmacodynamics is what the drug does in the body. The therapeutic effect is the desired effect on the body. You know, for example, antibiotics slow the growth and or reproduction of germs. Germs. Laxatives increase the rate of peristaltic movement. Okay, so it increases peristalsis within the gut, which moves the bowels faster. So, understanding what the therapeutic effect and understanding will give you an idea of the pharmacodynamics of that drug. So, an antiplatelet, the therapeutic effect would be to decrease platelet accretion. Sorry about that. The pharmacodynamics, it would make it an antiplatelet. So I want to talk about a couple more terms that are key here. One of them we talked about briefly. It's called the first pass effect. And that is the initial metabolism in the liver of a drug which is absorbed through the GI tract before it reaches systemic circulation through the bloodstream. Okay, so this is all about orally taken medications. Remember, it comes through the GI tract. And it goes through the liver, and that first pass through the liver will begin the metabolism of that drug before it gets distributed through the whole body. So the first pass effect is important because it can change the concentration of the bioavailable medication. So first pass effect is a key concept in terms of knowing how much medication to give for the correct dose and the correct response. there's also two more key terms: agonist and antagonist. Now, if you remember from your high school language arts, an antagonist in a story is the bad guy. Antagonist is the one that tries to cause problems and creates the trouble that the story's about. Well, that's not exactly what we're talking about here. An agonist interacts with the receptor to produce a response. Okay, so an agonist interacts with the receptor and it creates the therapeutic response. An antagonist doesn't really have its own pharmacological action, but it interacts with the receptor to prevent the action of an agonist. Why would you take a medication, a drug, that interacts with the receptor to prevent the action of an agonist? Well, maybe we're trying to prevent side effects or undesired effects that are being taken. Suppose a person is misusing a narcotic. We use a narcotic antagonist to prevent people from getting the pleasant feel from the narcotic. In this case, you're binding with that receptor to prevent that other drug from getting in there and making the person feel good or feel bad or feel whatever. So, looking at agonist and antagonist, an agonist is a drug that interacts with the receptor to produce a predicted response. Okay? Morphine interacts with the receptor in the nervous system to produce a reduced pain response. That's the expected. An antagonist is a drug that inhibits or prevents the action of an agonist. That's why we call it an antagonist. In this case, it's not causing problems. It's actually trying to prevent a problem. A couple more key phrases. Additive effect. Now, just think about it. Additive effect. Well, the effect is what is the result. Additive simply means when you take two drugs, the result of a drug interaction that occurs when two drugs with similar actions are given together. Boom. Additive effects. In other words, it's a case of 1 + 1 = 8. I know, it sounds crazy, right? Let's think about it, okay? Let's use pain pill, Vicodin, hydrocodone with acetaminophen. It's a moderate to severe painkiller. Remember the side effects of painkillers? The first one is to reduce pain. The second one is to cause sedation. The third one is to decrease respiratory function. What do they say never to take with a narcotic? Alcohol. So a person drinks some alcohol when they're taking a painkiller. Alcohol is also a sedative. Makes people drowsy, and it can interfere with respiratory drive. Take the two together, you get more than each of those individually. That is an additive effect. A synergistic effect. A synergistic effect, that additive effect is when you take two drugs that have similar results and increase it. The synergistic effect is actually what I'm talking about with the alcohol and the narcotic. That's when you get the 1 + 1 = 8. Sorry about that. Additive 1 + 1 = 2, so it's like you're taking a double dose of something. Synergistic 1 + 1 = 8. You're getting much more reaction than you would have expected from either one of those individually. Okay, additive, little bit increase. Synergistic, huge increase. Sorry about that confusion. And lastly, incompatibility. Incompatibility. What do you suppose we're talking about there? Well, that is when a drug is incompatible either with the person or with another medication. Warfarin. Remember, warfarin is to prevent the blood from clotting. Well, if you take warfarin and eat a lot of green leafy vegetables, spinach, for example, you will consume too much vitamin K. And vitamin K and warfarin are incompatible together. They neutralize each other. So you must watch out for drug incompatibilities. Come on back. We're going to talk about onset, peak, and duration. I know, the excitement just never ends, does it?